All right, let's go ahead and at least start talking about binary trees.
That actually has to do with this class too. You're gonna wipe out.
Trees are a very important topic inside data structures.
Trees are life.
Trees are life. Okay. Very important data structures. They are used a whole lot out in the real world to implement a lot of different things. Binary trees are definitely one of the simplest ones, so we're going to actually study that for a while. And your next project will be a study of binary trees. Now, a lot of actual trees are more advanced than just binary trees, but once you understand binary tree, you can kind of see how you can branch out to other other trees. All right, now those are some nice objectives. Okay. So a binary tree is either empty or has these properties. It has a root node and has two sets of nodes, the left subtree and the right subtree, and the left subtree and the right subtree are binary trees. Wow, that was amazing.
That's beautiful.
What type of definition is this?
Each tree is a tree?
Oh, bad definition.
No.
Every branch of the tree is another tree.
Yes?
It's a metaphor.
No.
To get to an actual tree.
If you were to call this either iterative or recursive, which would you choose?
Recursive.
Why?
It repeats.
Because of subtrees.
Because of subtrees, right. It's defining itself by using parts of itself.
Yes.
Right. So it's recursive.
It's using itself to create itself.
Okay, let me go ahead and draw a picture, because that always helps. And y'all like pictures, right?
Pictures.
I like the stereo. Ah, here's the...
You guys on this one?
All right. So you might have a root node. What value do you want it to have?
27.
15.
What?
That
Rude.
Nice.
27.
Thank
Now
you.
give me another number.
62.
That's less than 15.
5.
-1.
Then -1.
What?
Now give me a... Sure, why not?
Obviously. You just wrote it.
Well, that's right on the glare.
Oh yeah.
Oh, that was great.
Let's mark that this time.
All right. Now give me a number between -1 and 5.
2.
-3.
That's not in between them.
3.
2.
All right, give me another number. Any number.
62.
62. Where do you think 62 would go following this pattern?
27.
27.
To the right or to the left of 27?
To the right now, y'all.
To the right.
Right.
All right. How about 32? Where would that go? Oh, I'm being tricky.
To the left.
To the left of 62.
To the left of 62.
Yes. That's right. The left is when it's less than. Right was
Greater, less.
Yes.
Sweet.
So then where would 45 be?
To the left of 32.
45.
45.
To the right of 32.
There we go. I mean, y'all see?
But you're writing it to the left. I said.
Greater,
Oh, I
greater,
meant right.
less. I'm sorry.
Wow.
Greater, less, greater.
I meant right, but I said left.
Oh, I think these things happen.
I was like literally looking. I was like that way.
The other left.
Right.
And there's your root.
That is a good question. Why is the 2 going to the right?
That should not be a 2.
Yeah. Do 8.
7.
I meant 8. Totally
Yeah.
meant 8. That's definitely what I meant.
There we go.
All right. So the root is at the beginning. The root is either empty or has 2 subtrees to the left and to the right, which it does. Notice that 5 is also can be a binary tree because it has a subtree to the left and a subtree to the right. -1 is also a binary tree because it has a subtree to the left, aka nothing, and a subtree to the right, aka empty, because a binary tree can be empty.
Whoa.
No.
Null, right, null.
Hey,
All
look
right.
at that. So it's a tree made out of a tree, made out of a tree, out of another tree,
Out of nothing.
Sadness.
out of nothing.
Of nothing, right.
It's a space tree.
The space tree. All right.
I wish we could draw it the other way so it
Hmm?
actually looked like a tree.
I said kids next door.
Hey, look, a picture. Root node is the parent of B and C. Notice that unlike real life trees, they start at top and grow down here instead of actually having the bottom and growing up.
Why don't we draw
They're
it
a
that
hanging-
way?
They're a
If
hanging
it's called a
tree.
tree.
Because
It's
no
a
one does it
hanging
that
tree.
way. Yes.
Isn't this like the beginning of machine
They're
learning?
like
as well?
vines.
Beginning of machine learning. You can use trees to set up machine learning with nets and whatnot, if that's what you're talking about.
Yeah.
So yeah, you're coming up with a data structure that's
A vine.
going to closer resemble, neural networks or machine learning or different techniques as well.
Yeah.
So yeah, we're going towards that track. That's awesome.
It's a hanging tree.
It's a hanging tree, sure, or an upside down.
There's like a mountain that curves like this and the tree growing this way.
You got it.
Yeah.
Yeah.
Don't worry, we got this.
All right. So root node, parent of B and C, left child of A, right child, a directed edge. Ooh, I didn't draw my arrows because that is important.
Bum, bum, bum.
I implied my arrows.
I think we got it.
Well, the-
Implication is not okay.
The point is, if you're at 32, you can't go back up to 62. There's no arrow there. There's just an arrow going down.
Sadness.
Not exactly sadness. It's just how life is.
Can't go back to the past.
Yes?
At least you're not drawing boxes this time.
That was a good.
Right, I'm drawing
reference.
circles. Wow. Are the circles more pleasing
I like circles.
than the box?
Yeah.
Just remember, a circle is just a bunch of straight lines. You zoom in close enough.
No. Incorrect. Incorrect.
You can make a circle out of a bunch of straight lines, but not every circle is a bunch of straight lines.
It's not supposed to be either.
No. Wait, where'd you learn? Who says
No,
that?
no,
everybody
if
talking about
you do like enough times, it pretty much looks like a circle.
It looks, but it's still not.
It's not a circle.
It's still not a circle.
No.
Because a circle is defined as all the points, all the points beyond a center point given a radius. So you give a certain distance, as all the points between the distance of a radius forms a circle. All right, binary tree. So a binary tree on the left is with one node. Everyone cool with that?
Yep.
Binary tree B is with two nodes. C is with also two nodes, but it's on the right. And then D is also binary tree with three nodes.
But it's on the right.
Right.
Made it sound like he was mad about it.
Hey, look, other binary trees.
Whoa! What?
Magic.
So A, B, D. All right, you can just notice where the nodes are kind of filling out. These are just, basically, these are three different options if you were going to have one line, just a straight line going down of binary trees, of a binary tree with three nodes.
Ta-da.
Every node has at most two children, hence the name binary. All right, all right. Whoa. All right. So it's saying right now, hold on, get this in your mind. A node stores its own information, aka that number, and keeps track of its left subtree and right subtree using pointers. So what are the three things a node has?
Data and 2 pointers.
And 2 pointers. You've got, what was it, Malik?
As a similar to a linked list.
Similar to a linked list, except for
Except for
There's 2 pointers.
2 pointers, and they're not, in a doubly linked list, they were pointing to next and previous. Now they're 2 pointers pointing to
Three different decks.
I
two
actually
different
have a
children.
question.
Yes.
Oh, yeah, sure.
What would be a real application of using a binary tree?
Wow. Which one do you want?
Shoot me something.
Let's see. Well, if you had a set,
Because you said it's very much used in the real world, so I'm a little curious.
there's a lot of little problems it's used for, depending on what you want. If you had a set of numbers or a set of people, and you wanted to, set A and group B, and you wanted to know the intersection of the two, and you wanted to have a very efficient computation, if your set was represented, both two sets were represented using a binary tree, then doing the intersection is actually really fast. And we'll get to that in a bit. Mhm.
We're gonna code.
Because, well, what else are we going to do?
It's data structure.
It's data structures. All right.
Yeah, learn about theory. Come on now.
Theory. All right. So I'm going to go and we're going to do this first. I'm going to binary tree .cpp. All right, we're going to just copy over. We'll copy over quicksort. Oops. cp dot slash, what do I have? qsort, quicksort, copy right here, and then I'm just going to move quicksort over to binary tree.cpp, then we'll go ahead and gvim the binary tree. Great. I'm just doing this so I can just copy and paste the other code over for timing. There we go. We'll get rid of quicksort right now, and we'll just comment out this section. So now we even have code to generate a bunch of numbers. All right, great. This is beautiful. All right, so first off, we want a class.
Hold on, you deleted size.
All right, I'll put size back in. Binary tree. Is that better? All right, first off, you need to have a node. So we probably should define a binary tree node first. And what does this node contain?
Data and two.
Yeah, data and pointers. Let's go ahead and stick with our templating routine. So public, you have binary tree node on T. And we're going to find out if that's the correct syntax in a moment. But the node is going to contain, what did we say again?
Data and 2 pointers.
All right, so how do I type out the data if I'm templating on class T?
T and data.
Yeah, there we go. T and data. And then what else is it storing?
Pointers.
2 pointers. And what are the type of those 2 pointers?
Node.
A binary tree node, right. So binary tree node, pointer m left, and pointer to m right. Boom. All right. And we'll have the default constructor take a constant t at ref or val. That way we can set m data equal to val, and we can have m left and equals m right, which will equal null. All right, let's see if I actually did that correctly, because that might not be the case. Oh, I did. That's amazing. Oh, actually, it may actually be completely wrong. Let's go binary tree node sub. We'll do it on integers, b node, and we'll have it start at 10. Let's see if it compiles. It did compile. Wow, that is amazing. All right. So we have a binary tree node. So that represents a node in the binary tree. If we wanted to have a class that represents the entire tree, we'll go and create a separate class for that. Notice how I've divided out the labor a little so that, excuse me, the node is its own class, so it's going to take responsibility of a node. Let's go ahead and make a class binary tree. And what is the binary tree going to have? A node, a. Now, is it going to be a node or a pointer to a node? Right, so binary tree node, and what should we call it? Tree, okay, those are good guesses. We should actually just call it the root.
Yeah, I guess it's better.
It's confusing because roots at the bottom.
Hmm?
Kind of confusing because roots at the
So
bottom.
that's like the head, right? Like first.
That's the first one. That's, if you go back to our picture, notice it's pointing up here to the 15, right? So we need to know where it begins. So that's where the root is. Let's go and give it a good default constructor, and it's actually going to set mroot to null. Why is that legal?
That's the pointer.
It's a pointer, and we've defined a binary tree as an empty binary tree as being a legal entity. So empty binary tree is legally a tree. All right.
It's like a tree with no leaves.
No leaves. Let me go and add these other templates to it so everything looks fine. It's not binary tree node as a constructor, it's just a binary tree. And let's go down here and let's on integers, and we'll just call it the IB tree for lack of a better word. Let me make sure that compiles. Wow, that's amazing. I have a hard time believing this is working.
That's the binary tree function as a constructor.
That's the constructor.
Yeah, constructor.
Right now, I'm just dumping it all in one file just to make my life easier for now. Obviously, in your labs, you need to divide it out. But I just want to make sure it's all on one page so you can see it. And y'all have not been stopping me to comment my code.
Oh yeah, please do that.
Please do.
So this represents a single node in a binary tree. All right, so the value of the node, pointers to the left and right child or children of the node.
But you could just call them subtrees, right?
Left and right children, yeah, sure, subtrees. Subtrees. Children, subtrees. Yeah, we'll go and make it a slash. That's even better. Slash subtrees of the node. So, let's see. Constructor to create a node based on a value. All right.
Why do you do that like that?
Just to keep showing you that there's two ways to do it. Usually, if I'm commenting at the end of a line, I use a single line comment. If I'm commenting above something, I'll do a multi-line.
Oh, except for the first one. It's-
You are correct. Let me be consistent. There. Represents a binary. I'm going to go ahead and call it a binary search tree. And we'll talk about what that means in a minute. But what's funny?
We were there.
All right. And this is a pointer to the root of the binary tree. I'm going to call it BST. I'm going to go up here and put BST. Boom. Binary search tree. All right. Default constructor to make the tree empty.
Do we need a deconstructor?
Do we need a deconstructor?
Probably.
Probably. We'll get to that hopefully in a minute.
Assumption.
All right, so binary tree node stores it. Up here they're calling the left link and the right neat. I'm calling M left and M right pointers. Great, we have that. So a pointer to the node of the binary tree is stored outside the tree in a pointer variable. That's what we just did over here. Here's the extra pointer variable inside of the class binary tree. So you can get to the root and then you can go and search down the list to see what's in it. All right, a leaf is a node that has no left or right children.
It's depressing.
It's depressing. It has no children.
Doesn't have children.
So what would be the leaves of this binary tree?
-1, 8, 45.
Everyone see that?
The leaves of the tree. It's stuff that
Oh,
doesn't
yes.
go on.
That doesn't have any children. No children.
I call that sadness.
Use a parent of V if there's a branch from U to V. All right, what's the parent of 8?
5.
What's the parent of 62?
27.
All right, anyone besides Sydney and Caitlin. What's the parent of 32? 62. All right, any other questions? Y'all following? Great.
Numbers.
Numbers are awesome.
Numbers are
The length of a path is the number of branches on that path. So what's the length from 15 to 62?
2.
Yes. How about from 27 to 45?
3.
All right. From 5 to 8?
1.
1. From -1 to 45?
0.
No, undefined. Yeah, there's nothing.
Does not.
Not legal.
They are not friends.
They are not friends. All right. The level of the node is the number of branches on the path from the root node. So the root node level is 0. So then what's the level of 8?
2.
And the level of 32?
3.
So the level of 62? All right. Anyone else? That's its level, the number of branches from the root. All right. The height of the binary tree is the number of nodes on the longest path. Number of nodes on the longest path. Is that what it said? Let me make sure.
Yeah.
Number of nodes on the longest path from the root to the leaf.
5.
5. Right.
Because you include the root, right?
Yeah. We're going to include the root. All right. I'll try and remind you of this terminology again, but it is important to keep it straight because it's what you're going to use in order to do your big O analysis of a binary search tree.
So don't be silly, get it right.
Yeah, well, sure. Binary tree is a dynamic data structure because memory is allocated and deallocated at runtime. let's go ahead and do a put function. Put binary put. Do I need to put the template right there? I forgot if I did. T put const t at val. Alright, so if we want to put something in this, and we're going to do it with a binary search tree, so we're going to enforce the ordering. How are we going to go about doing that? Well, first, create a node. Alright, so 1, create a node. Great. After we create the node, what are we going to do?
Decide if it's greater than or less than the values that we already have.
Alright. What? You're on the right track, but what do we need to do before that? What if the tree is empty?
Check to see if
Create a
there's
new
anything.
tree, or start a new tree. Put the root node
assign
in.
that root.
Yeah, assign root to that node. So, 2, check if tree is empty. Actually, boom, boom, boom. If empty, assign root to node and return. Oops. Okay. So if not empty, what are we going to do now?
Assign it to wherever place it needs to go.
All right. We need to determine where it goes. Oops. Where it goes and assign. All right. Let's see if we can do it from there. So first off, create a node. All right. How would we create this node?
Would we use your binary tree node?
Right. So we need to go binary tree node sub t. It's going to be a pointer because we're storing pointers equals new binary tree node passing in val. All right, let me make sure that code's correct. That's amazing.
I don't think you keep getting just like amazed at your code.
Because I've done this way too many times, and I just don't trust C++ anymore.
What's your favorite data structure?
There we go. What's my favorite data structure?
The sadness data structure.
I don't know. I don't know what my favorite is. All right, request for member put in IB tree, which is of non-class binary. Put. And binary, which is, did I not call it put? I did call it put. Does it need to have a T right there? Is that the problem? Nope, I didn't think so.
That created more.
I did create more problems. Alright, so we need to ibtree.put75. Alright, let me find out what these errors are. Alright, error request for member put in ibtree, which is non-class type. What does that even mean? Doesn't make sense. Put 75. So we're declaring put right here. It's a binary tree. I called IB tree, passing in nothing, and we're putting 75. Constant value.
Maybe it doesn't like templates.
That is a very common problem. That's usually what the issue is.
Wait, so for that function, you don't have to put a, like, what type of function it is? In the-
Well, the template's up here, and you're defining it directly in the header. So it should actually come right up.
Oh, I see.
But what it's saying is it's not able to reference put from IB tree, even though it's right here, which is actually quite confusing. Let me make an add function real quick and see if I can figure out why C++ is doing this. Because it should do, yeah, member add, which is non-class type binary tree int. Non-class type.
Google.
That does not make any sense. Yeah, we'll do that. There's just something silly I'm doing wrong. Okay.
Google actually worked out for once.
It has failed me. All right. Ooh, Stack Overflow. Oh, this is beautiful. This will make it even better.
Stack Overflow?
Stack Overflow. Why else would you not use? Put tag string. What's the problem? This line does not what you think. Does not do. Oh, does not do what you think. Oh. Ha.
How?
Ha.
Wow.
Thanks, C++. So it was declaring a function called IVTree. Now I'm actually declaring the class on the stack. Oh, that was a fun one. All right, thanks, C++.
Wow.
That's dumb.
That dumb. All right,
I love it.
dumb. Okay, if the tree is empty, the tree is empty, what do we do? How do we check if the tree is empty?
If the root is pointing to no,
Oh.
to null.
If the root is pointing to null, then what do we need to do? Malik? And root equals node and then return. Yeah. That's what I heard you say.
Yeah, that's true.
All right. Okay, so that takes care of that. If not, we need to determine where it goes in a sign. Oh.
Oh no.
How should we do this? Let's think. How do we figure out its location? Well, huh?
Wait.
Pointers.
Checks.
So we have pointers. The last time you had a pointer structure, like with linked list, what did we use to go through it?
Rover.
Rover. So what should rover be?
Red Rover?
Not red rover. So rovers. Rover should point to a what? What should rover point to? Should point to a node. Okay. You were thinking it, you just weren't saying it explicitly, which is fine. So we will have binary tree node t star rover, and he's going to initially point to root, right?
Yes.
All right, let's do that first. So we're going to have binary tree node t star rover equals m root. Great. Okay. So if we were going to, let's say, put, what would be a good value to put in there? Let's put in 10. And I should put this on that side so I don't convolute everyone. Actually, we're not putting in 10. We're going to put in 87. That way, things don't get too bad. So if we're going to go put on 87, if we're looking at 15, which way do we go? Right, okay. So then it would go over here. Looking at 27, which way should we go?
Right.
Right, so then it would go over here. So this is 1, 2, 3. We're at 62. Where do we go?
Left.
Hold on. Is it greater than or less than 62?
Less than.
Is 87 greater than or less than?
Greater than.
Greater than. So we'd want to go right, except for.
There is no right.
So what would we do?
Create a new node.
Create a new
Yeah,
node.
that's where we would. That's where we want to create our new node. So that's what we want to do. So in other words, we want to start at 15. We want to decide if we need to go left or right, and as long as we can, you continue on.
As long as you can.
Right. Okay. So how's that look in code? So it starts at root. So what do we need to do? We need to check if rover is less than / greater than value. Okay. Then see if there is a node there. We should say if there is a node on that path, move rover down and iterate. And iterate. Although we could iterate. What else could we do instead? What actually would make this a whole lot easier? Pointers.
Pointers.
So we could do it iterate. Move rover down. Yeah, and recurse. There we go. So let's go ahead and set up the recursion. I'm going to go ahead and help you out by doing void put. We'll do binary tree node t root star root and binary tree node t2 to add. And this needs to be a private, that way no one else calls it. That way it's a helper function. So basically what we're doing is we're going to first check if the node needs to be root. Now call the recursive function to add the node to the correct location. So we're going to do that by doing put, sending mroot, and of course our node that we have created. And then the rest of this, we're going to go up here. Oop, not right there, right here. All right. So in actuality, this isn't root, this is rover. There we go. So that's what rover is going to be. So rover is going to be passed to this function. Determine where it goes in a sign. All right. We need to check if rover is less than or greater than that value. Okay, let's do that first. If rover, it's a pointer, dot, whoops. What are we checking? What? Data. All right. mdata. We'll say if it's less than 2 add dot mdata. If it's less than, which way do we need to go?
Left.
To the left.
So let's say if rover's data is less than mdata, you need, okay, maybe we're thinking of that backwards. If 15 is less than 87, which way do we need to go?
Oh, 15 is less than
Right.
87.
Right. Okay. So let me type that the other way because I think I did confuse y'all with that. So if to add, the data we want to add is less than rover.mdata, maybe that'll make more sense.
Yeah.
If this number is less than mdata, we want to go left. All right.
That makes more sense.
Okay. So then we just do put on rover-m left, comma, to add. Right? Okay.
Sure.
Sure. Otherwise, what do we do?
Put it on the right.
Put rover-m right to add. Does this actually add something yet?
No.
No.
It's just moving over.
It's just we've set up the tree so it's moving down or recursing down. When do we actually check to see if we can add something?
When the points are null.
Right. So if rover-m left equals null, then we just want to do what? If we find we need to go left, but that left is null, what are we doing?
You gotta
Gotta
create
add it.
We already created the node, so we just need to add it. So rover-m left equals to add, and then we return. And then on the right-hand side, what do we do?
If the right is equal to the null.
Then you add the to add, then you return. So let me go ahead and comment this a little more. So let's see, if not empty, we need to determine where it goes in a sign. So we need to first check if rover is less than, all right, or greater than. If less than and left is null, add the node and return. Otherwise, recurse. Did I spell recurse?
Yeah.
Okay. Down the left side. All right, and this is actually going to be the same thing. If
So does that check both the left and the right of the how 5 has -1 and 8, would it check both sides?
Hold on, let me get these comments in before I forget. Okay, what's your question?
Okay. So would this check both the left and the right side? Same with like 5, how it has -1 and 8. Would it check both sides there?
Okay, so if you are at 5, let's put in a number. What example number would you like me to look while we're evaluating 5? So it'd have to be less than 15.
12.
12, okay. So if it's at 12, rover starts at 15. It's less than, so then rover would go over to here, 5. It'd look at 5. 12 is not less than 5, so it's going to go to the right. That node exists, so then rover is now going to be up. Basically, we're going to recurse and add rover 3 right here. Okay? Now we're at 8. We ask, is 12 less than 8? No. So we need to go to the right, but right is currently null. So we instead use that node that we created and put it right here. Okay?
Yeah.
We gotta start thinking recursively, because with binary trees, a lot of the algorithms are a lot easier to solve if you use recursion. A lot easier to solve. Okay. And for the sake of clarity, I'm going to make a little memory stack here.
Hey, it's actually decent fun.
All right. So you call put right here of our tree with the value 12. Ah, foreign policies. Are you considering binary trees foreign? Is that the problem?
Yeah. Just pop up, sorry.
Foreigners. All right. That was just a joke. Just a joke. Just a joke. All right. So when you first call it, you have rover pointing to 15, and we'll just have to add pointing to some, we'll just say some node that contains 12. Let me map over to the code to show you what that means. When you first call put, which is down here, we create that node. Right here, I'm calling it to add. So there's that node that we just created up there. And then, of course, rover, we check to make sure root is not null, because if it is null, then we just set that as our new binary tree and get out. Otherwise, we're going to call put passing mroot. So rover initially will point to mroot. So that's rover pointing to mroot, and to add is going to point to that node. Okay?
Yes.
All right. I want to make sure this recursion is clear, because this has got to start being crystal clear. So on first call, we have rover pointing to root, to add pointing to that node. We ask if the data is less than the rover dash data, aka is 12 less than 15. The answer is yes. Is there a node to the left of 15?
Yes.
So is less than 15. Is there a node less, or not a node less to 15? There's not, so it's going to go and recurse by calling put with rover m left and to add. So now we're going to call the function again, but this time rover is going to point to this guy over here. And to add is going to still point to that new node. Okay? All right. So we're at that point. Let's see. Rover's pointing to the 5 right now. Is 5 less than, what are we adding? 12? No. So we're jumping here. Is the right null? So we're at 5. Is the right null? No. So we're going to go ahead and jump out of, not go into that for statement, go into the recursive where we're going to call passing m right. So now we're going to, oh, that was terrible. Let's get an eraser for that. We're going to, again, another rover pointer. This time he's going to point to the 8 and to add it's still going to point to that new node. All right? Now, at this point, let me erase that because that hasn't happened. We're going to ask, is 12 less than 8? No. Jump down here. Is the right null? So we're at 8. Is the right null?
Yes.
Yes, it is. So we're going to set its right equal to that new node, which is really this guy over here. You know, he's really pointing. I know it's a lot of Arab guys, but pointing to that. It's just somewhere in memory, right? All right. What's important to understand is what's happening here. What is this over here? Every time you call a function, what does it do? It appends a new rover pointer, a new add pointer to it, correct?
Yeah.
What data structure is this?
A linked list in a sense?
A linked list, correct, but more specifically, what is it?
Doubly linked list.
Singly linked list.
Okay, it's not an array or a linked list. That's all I'm looking for. What's the other data structures we used?
Stacks and queues.
Right, is this a stack or a queue?
Stack.
It's a stack because it adds to it, and then that's the new guy on top. So when you recurse, notice that when you come back, you're going to actually jump back up to this rover and then back up to this rover before you're done. Okay? It's very important you understand that.
Now can you reverse a binary tree and make it like a queue somehow?
Make it a queue. You can use a binary tree to implement a queue.
That's cool.
And I'll show you why that's pretty important. All right.
Oh boy.
Any questions about this example? I'm going to go through another one to show you why recursion is so useful here. All right, so we can add a bunch of data. And you know what? Let's see. We have some numbers. Let's go ahead and add them to the binary tree. So for int I equals 0, I is less than 10, I plus plus. We'll just do ib tree.put, and we'll go number sub I. So notice I've already created a bunch of numbers up here with making them random. Let's just go ahead and put them in there and see if we get a good old seg fault. Or if nothing happens, or if it doesn't even compile. That's always a good situation as well. Let's see what we got here. Instantiation required here, int boolean mdata is private. Oh, it's private. Oh, because the binary tree node is not part of it. So let's go ahead and give it a quick little public function. T get data, return mdata. There. Now I can at least read it, although it can't set it. So when we're over here, we're going to just call get data. You understand what I did there? Just created a public getter so I can get a hold of that data of the node because it's private. Everyone okay with that? You okay, Malik?
Yeah. So you went public with the data.
Yeah, you don't want to be public with the data. All right,
So
let's.
now it's open source.
All right. Whoa, we got another problem. Get rover mdata. Oh, to add. Oh, I didn't do it with the other side. Oh, also the left and the right aren't there. Oh, man. Okay. So in reality, what we want is we don't want that as part of the, we don't want it outside is what it is. We want to make it part of the binary tree itself, which is legal inside of C++. So we're going to get rid of that. Let me make sure that didn't cause any problems. Non-template type binary trees used in template binary tree node line 20. Line 20 binary tree node class. Let's see. Oops. What? Is that what it wants? It might be what it wants. No.
Whoa.
Wow, okay. We're going to not do that, and I'm just going to... Whew, that's bad. All right. We'll just make it all public, just to make my life easier.
But will it make our lives easier?
So will you need that
Wow.
get data function then?
Yeah, I just removed it. We won't need it. We're going to have to remember how that previous code was done. So I'm just going to make it all public. Recompile. There, see, it worked. Yeah, scoping issues. All right, so it compiles without a seg fault, so that's good. We aren't seg faulting. And put the numbers. Fortunately, we need to somehow print them, don't we? Print, right? Print. All right. Let's see. How are we going to print this? We'll go. I'm just going to call void print. Ooh. So how do we print this?
Kind of like the way you would do with a linked list.
Okay.
You would start from the top and work your way all the way to the left.
Okay.
And so it'd be 15, 5, -1, and then it would be 8, then 27, 62, 32, and 45.
So there are different ways to print this. If you want to print it in order, how would you print it?
15, 5,
No, you want to print it in order, so you want to print the smallest number first.
-1,
-1, then you would print
8, 5,
5, then you would print,
8,
then you would print.
12.
Okay, if the 12 was right here, yes, you'd print the 12,
Then
right.
it'd be 15,
15,
27, 32,
Yeah, that one.
30,
45.
45, then 62.
45, 67.
That would be annoying to actually do.
So it's very annoying to do this iteratively. The recursive solution is actually very simple.
I like this iPad. I like the chair higher. I actually can see more.
So first off, I'm gonna basically show you why the recursive, just show you the recursive function for this. So if you want to put or print, really the first thing you want to do is have the recursive function that prints. So we're just going to have void print being past a binary tree, no template on T. So I'll just call it we'll call it rover.
So when it comes to our data structures now, recursion is the way to go.
It depends on your data structure, but for binary trees, a lot of solutions are far easier recursively than they are iteratively. Now, for other data structures, like when we go into hash tables, the recursive solution is not as pretty as an iterative one. You have to sit down and decide which ones you want to use. I'm using recursion because we all need to learn recursion. It's a tool a lot of people forget about.
What's recursion again?
What is recursion, Craig?
Where you call a function many times.
Function calls itself. Binary tree, print.
Would you say it's better for like a linked list?
It depends on what you're doing. I can't just, there's no general yes or no. You have to really evaluate what's going on. So if we're going to print binary, I'm going to call it in order print. So I should change this to in order print of the node. Well, if we're at rover, we want to just traverse. Actually, if we want to traverse, let's do the base case. What's the base case here? If rover, when do we stop? Do we print null? No. So if rover is null, return. So 1. Oh, okay. One moment. Take care of the base case. Go ahead. Come on in. So we're going to have a special guest for us real quick, Valerie Sessions, and she's going to explain to you why all of y'all should go to...
Not all of you. So